It's my great pleasure to introduce our speaker today, Jeff Thompson from Princeton University. So Jeff started out in physics research as an undergrad at Yale with Jack Harris, where he did some pioneering work on optomechanics with silicon nitride membranes. He then did his PhD in the same group as me, in the Lucan group at Harvard, where he did some pioneering work again on trapping single atoms and coupling them to photonic crystal cavities. He did a very brief postdoc at MIT where he did pioneering work on engineering light matter interactions in Rydberg gases. And he's now at Princeton where he's doing pioneering work in a number of different fields. But today he'll be telling us about rare earth ions and doing atomic physics in the solid state. He's received a number of awards. I'll just list a few of them, including he's a Sloan Fellow. He's a recipient of PCASE. I won't mention what that stands for. And he is a recipient of the DOE Career Award. So with that, Jeff, please go ahead.
Thank you very much. I assume you can hear me. And I want to start by saying thank you to the organizers for the invitation, but also for putting this thing together in the first place. I think it's been really a great asset for the community during this time, and I've enjoyed many of these seminars before this one. So today, what I'm going to tell you about is a kind of a set of research efforts in my group that are kind of built on sort of a pretty simple premise, which is that we do a lot of really neat things with atomic physics systems, ranging from quantum simulation to kind of looking at quantum optics to quantum information applications. And wouldn't it be neat if we could do this stuff instead of using atoms that are laser cooled and say laser trapped, levitated in ultra high vacuum chambers, instead using atoms that are essentially trapped in place in a solid crystal. And so the technical motivation for doing this is pretty straightforward. It's that laser cooling and trapping is sort of a real pain in the neck, and it would be nice if you could get rid of it. But beyond this technical advantage, there's actually some really fundamental opportunities that are afforded by working in the solid state. One of them is that you can bring things together at higher spatial density. Densities are just higher in the solid state, and that gives you a route to engineering much stronger interactions than you might be able to have with more dilute systems. And the second is that the solid state is the realm, where devices live. And I'm thinking here of things like, photonic devices, electronic devices like transistors, localized mechanical modes and things like that. And being able to integrate atoms with devices also gives you some kind of fundamentally new possibilities for functionality, whether it's having, very strong, light matter or phonon matter interaction that might let you do, say, very efficient readout, or using this kind of interactions with like an optical cavity, for example, to mediate interactions between spins and things like that. So there's a lot of opportunities, I think, to basically trying to do atomic physics in the solid state. But now there's, of course, an obvious downside too, which is that some of actually, when you think of quantum simulation, you actually think about really trying to get away from the solid state and to try to do beautiful physics without the solid state with itself, which is actually dirty and disordered and just generally very complicated. But nevertheless, what can we do? So this is, of course, not a novel idea, and in fact, it's a direction that's been really actively pursued for the last 20 or so years, I would say, and it's fair to say, I think, that the vast majority of this work has been done with a particular atom-like defect in the solid state, which is the nitrogen vacancy or the NV center in diamond. This is the rubidium atom of solid state defects, if you will. And what this is, I've actually stolen this picture from Shimon's webpage because it's one of the highest, first things that come up in Google. So just like, if you have atoms, trapped in vacuum, you illuminate them with a laser, they fluoresce, and you can image the fluorescence. If you illuminate a diamond here with green light and you collect the fluorescence, you see, if you zoom in, you see a series of points, since the fluorescence originating from individual atomic defects. In the case of the NV center, what these defects are, it's a diamond, and you've replaced one of the carbon atoms with nitrogen, and another one you've replaced it with a vacancy, which is to say you've gotten rid of it. And this complex here is an atom. And so what do we mean that it's an atom? Well, we mean it walks like an atom, it talks like an atom, it has a spin, it has optical transitions, and then you can use the optical transitions to manipulate the spin. So you can do things like optical pumping, fluorescent readout of the spin state, and things like that. But all with this thing in the solid state. And these systems, and the NV Center in particular, has found incredibly wide applications to things ranging from quantum networks and other tasks in quantum information to sensors of various fields, magnetic fields, electric fields, temperature, And then also kind of to go and explore physics, like for example, the dynamics of a strongly interacting system, things like many body localization and time crystals, really leveraging the density that you can get in these systems. And this work is not actually completely limited to the NV Center. The NV has a few close cousins that people also study, like other vacancy centers in diamond, like silicon vacancy, germanium vacancy, and then kind of analogous centers in silicon carbide and other wide bandgap semiconductors. But this type of defect is actually not the only type of atomic defect that you can imagine using. It's not the only type of trapped atom in the solid state you can imagine using to try to do atomic physics sort of things. And I actually like to kind of take a step back and maybe kind of classify what the range of ways you can do this is. And basically, at the end of the day, for something to look like an atom, you've got to have some localized electronic state, and then transitions between different states, and that's what an atom is: localized electronic wave function. So how can you localize electronic states in solids? Well, one way to do it is to make a quantum dot, where you actually have a material, basically put a particle in a box in some sense within a semiconductor. So you have an island of one semiconductor inside another, and in this case, the electrons, they really live in the conduction band or the valence band of these semiconductors, and they're just confined, spatially by this material boundary. You can make color centers. Where you have basically all color centers have as part of their ingredient a vacancy, and when you have this vacancy, you have now from the host lattice dangling bonds sticking in. In diamond there would have been a carbon where that vacancy was. Now there's nothing, and so the electrons that are responsible for the spin and the optical transitions in these color centers primarily actually live on these dangling bonds. And so in some sense, you could say that these electrons are really, they belong in the host crystal, but they're just pinned in place by the defect. So the properties of these kind of color centers really come from a combination of what is this defect that localized the electron, but also what is the crystal around it. And then a final kind of atom that you can have, which is what I'll talk about today, is a rare earth atom. And the rare earth atoms, if you remember, they live down here, sort of at the bottom of the periodic table. And what's the reason they get their own island is that you have this unfilled 4f electron shell. But what's unique about the 4f orbitals is that they're very closely bound to the atomic nucleus. They don't really participate in bonding. So when you put these rare earth atoms into crystals, these electrons basically are unaffected by the fact that they're in a crystal. And so so with this taxonomy, what I'm going to say then is you go from left to right. You basically go from electrons in a conduction band trapped by a solid to really having just atom to really just having an atom like the atoms about in free space, but just pinned in place in a solid. So things become more atom-like as you go from left to right. And of course, the problem with being in the solid state in the first place is that the solid is dirty and messy. And so my general claim that I'm going to try to support later in this talk is that by moving further to the right of this, you have, you get more atom-like properties, cleaner systems to play with. And of course, there's a few other kind of categories of defects, like transition metals that sit somewhere in between color centers and rare earth ions, things like that. Okay, so as I said on the previous slide, the thing that's special about these rare earth elements is that this 4f shell, where the active electrons live, just is not affected by the kind of the solid state environment that you put it in. And I think the number that illustrates this for me the best is that what I've shown here is these red lines. It shows, this is a scale drawing. It shows that energy splitting between the ground and the first excited electronic state of an erbium 3+ ion in vacuum. This number is pulled from the NIST database. And then what I've shown here in black is what the energy levels of an erbium 3+ ion in a particular host crystal, the one that we'll be using in this talk. And what you see is that this splitting is basically unaffected by the fact that you put this thing into a crystal, which is pretty remarkable. The only thing that happens is that you lower the degeneracy of this pretty high spin ground state into lower degeneracy into less degenerate states, because you're no longer in a spherically symmetric environment. You have a lower symmetry environment in the solid. But other than that, this atom still basically looks like it would have in free space. It's recognizable even though you put it into a solid crystal. And this is not true of transition metals, and certainly not true of the NV center. The nitrogen vacancy center has nothing to do with nitrogen. So again, the things that are attractive about this are, first, that all the kind of the properties of the system really come from the atom. So if you pick an atom that you like, then you will get the properties that you thought you were going to have. because it's not really that affected by the host crystal, you can actually put these things into, in principle, any host crystal you want, and also at any concentration you want. So that gives you sort of a pretty significant engineering degree of freedom to play with these systems. If you see, a lot of, it's basically like engineering a trap. You can engineer many different traps, and you might think that different ones would be better for different applications. The weak coupling of these 4f electrons to the environment around it means that you are kind of shielded from nasty effects in the solid. And the main thing that shields you from is kind of vibrational coupling, and in particular, this suppresses sort of non-radiative decay and what's called the phonon sideband, which is a particularly bad problem with the NV center that most of the time when it decays from the excited state, it doesn't just emit a photon, but also a phonon. And so it's not the spectrum is not very clean. Some additional kind of benefits that we'll talk about later are that these rare earth atoms, are typically very magnetic, and so can have big magnetic moments that let you engineer strong interactions between them. And I'll talk at the in the sort of second part of my talk about some techniques that are kind of particularly easy to apply with these rare earth atoms that let us address a lot of them with very close spacings, far below the diffraction limit of light. And so these two things together are really kind of unique possibilities for this system to create strongly interacting systems. So the particular rare earth atom that we're going to focus on in this talk is erbium, which is always going to be in its in a 3+ charge state when you put it in crystals. The Hamiltonian of this, it's actually, it's a little, this 4i 15/2 free atom term symbol is maybe a little bit scary because it has a 16-fold degeneracy. That's a lot of spin states. But when you put it in this low symmetry crystal, in general, it's always going to split to lower its degeneracy into 8 doublets. Lowering any further is prohibited by Kramer's theorem, by time reversal symmetry. But then, and the kind of the scale of this splitting is, let's say of order of a few terahertz. So each of these levels is now 2-fold degenerate. And then if we apply a magnetic field, you lift this degeneracy further by an amount, Zeeman splitting, let's say it's of order of gigahertz. And so at the end of the day, the level structure that we can think about, we can kind of forget about all of this stuff and just think about a spin 1/2 ground state and a spin 1/2 excited state. It's a very simple atomic structure at the end of the day. And so when we talk about a spin, we're thinking about manipulating the doublet ground state crystal field level. And we talk about an optical transition, it's to the lowest crystal field level of the first excited state. The reason we're particularly interested in working with erbium is that it's kind of unique among atoms in that it has an optical transition at a wavelength of 1.5 microns, which is the so-called telecom band, where optical fibers have their lowest loss transmission window. So for quantum networks, that's very advantageous. But also you can integrate it with silicon photonic devices, which we'll use to great advantage in this work. It has a particularly strong magnetic moment, depending on the host crystal, 5 to 9 Bohr magnetons for interactions. And it has a bunch of zero nuclear spin isotopes, which lets you keep this nice level structure. If you add a big nuclear spin, this gets very messy. So there's two kind of applications that we have in mind setting out with this work. The first one is developing a single photon source and quantum memory to use for long distance quantum networks. And here, beyond just having a nice radiatively efficient transition and potentially long coherence in the ground state and things like that, the real advantage of using erbium for this is actually this transition wavelength at 1.5 microns. And to kind of hammer in the advantage here, the hard part about quantum networks is actually overcoming loss. Basically, photons are absorbed, they're attenuated exponentially in optical fibers, and essentially all you're trying to do is correct for the error that introduces. If you didn't have any loss, quantum networking is pretty easy. So quantum repeaters and things like that are designed to get around this loss, but the loss depends strongly on wavelength. And at this the so-called telecom band, where erbium is, the transmission over 100 kilometers of fiber is about 1%. If you go to the NV center wavelength, it's actually 10 to the minus 80. So right away, you have this sort of 78 order of magnitude advantage, and that's just going 100 kilometers from moving to this wavelength range. And this is, of course, why the erbium doped fiber amplifier is sort of the backbone of classical long-haul communications networks. And the second kind of direction that we hope to extend the system into is actually to be able to make strongly interacting sort of clusters of spins, maybe 5, maybe 10, maybe 100 erbium atoms that talk to each other through a magnetic dipolar interaction. They might each have their own little bath of resolvable, countable number of nuclear spins that they talk to additionally. So you can actually build up a fairly complex system here. But the kind of, but the key thing that makes this really interesting with rare earth ions is that, first of all, you can get them together at pretty high density and have these big interactions with their strong magnetic moments. But second, we have a pretty unique technique for kind of doing some kind of frequency domain super resolution that's actually going to let us address these ions, even if they're separated only by tens of nanometers, which is where these interactions become really strong. And so with this kind of system, there's a few things that I think will be interesting to explore. The first is actually just fundamentally figuring out, okay, if I create some instance of this strongly interacting system, how do I do spectroscopy on it? How do I figure out what the Hamiltonian is? This is a little bit reminiscent of doing kind of structure determination with NMR. And the second is, given that I've now mapped out what the kind of Hamiltonian governing the system is, can I do some kind of quantum controller Hamiltonian engineering by driving the system to basically turn off some interactions, shape this evolution into something arbitrary or something different from the native Hamiltonian. And then if I can do that, then can I actually turn it into something useful either for quantum simulation or maybe for quantum information processing? And a pretty low-hanging application for quantum information here would be to use multiple erbium atoms together in a single device to do some kind of error-corrected multiplex quantum network in connection with what we discussed on the previous slide. So we are, by no means the first people to go and try to do, atomic physics-like things with rare earth ions. There's actually a long history. I mean, actually, these systems were really studied in the first place in the context of laser development, in the 60s and 70s. And I'm sure all of you have either erbium or a terbium fiber laser or a neodymium YAG laser in your lab somewhere. It's a rare earth laser. But in the context of sort of atomic physics or quantum information, the earliest work in this field was in making quantum memories for light using sort of rare earth ensembles. So these are crystals that are doped with pretty high concentrations of rare earth ions. It's sort of the solid state analog of a vapor cell. And these experiments have, it's actually a promising approach to quantum networks in its own right, but they've also demonstrated some really intriguing properties of these rare earth systems, including, a couple of records for sort of coherence times for solid state spin systems. For example, a quantum memory with a 6-hour coherence time was demonstrated with europium nuclear spins in a europium doped crystal. Europium being another rare earth ion that has this beautiful yellow transition shown here. Another application that is pursued with rare earth ensembles is doing microwave to optical transduction to connect single photons from the microwave domain from superconducting circuits, for example, to optical photons for example, connecting together superconducting circuits. And a third application that actually really leverages the sort of the high degree of isolation and stability of these 4F electron transitions is laser frequency stabilization. In this picture here, we see the transmission spectrum through, I think this is again a europium doped crystal, where you can basically burn a series of spectral holes where you change, you induce a sort of a kilohertz wide, transparency or absorption window inside this crystal, and this thing stays stable for hours. This line will not move. If you leave it alone, this transparency feature will still be there many hours later when you come back to probe it. And so this NIST group explored quite successfully using the stability of these optical transitions as sort of a short-term frequency reference as an alternative to an optical cavity for laser frequency stabilization. So these things have been studied kind of extensively in ensembles, but within this community, going to explore single rare earth atoms in the way that most of the experiments, with NV centers work, has been a longstanding goal, but it's actually also a longstanding challenge. And the reason for this challenge is that transitions between different 4F electron levels, which are the transitions that are shielded, so should have these nice properties, are all parity forbidden because both the initial and final states have the same number of F electrons, so the parity is always the same. So they're electric dipole forbidden. So nothing is really forbidden in quantum mechanics. There's a magnetic dipole decay pathway, and if you're in a crystal, you can have a little bit of forced electric dipole from the strong crystal fields. But generically, these rare earth atoms have excited state lifetimes that are of order 10 milliseconds. So that's about 1 million times longer than a typical allowed transition. It's more like 10 nanoseconds. And so, so that basically can make your experiments 1 million times harder. So that's not good. So there have been some, heroic experiments on just basically trying to do brute force confocal microscopy of these things anyways. And so this is an image with, essentially these count rates of some praseodymium ions in, I think, YAG. And there have also been some really neat work that I think leverages, again, what you can do with devices in the solid state, where people did some kind of optoelectronic detection of single erbium ions in silicon, but not detecting fluorescence, but actually exciting them optically and then measuring the charge using a CMOS transistor. So that's kind of the state of the single rare earth ion field. So where we came into this was to say, well, if we could really fix this lifetime problem, then we could have a very nice platform to work with. So I want to remind you that the lifetime of say the decay rate of the excited state of this atom is, according to Fermi's golden rule, the product of two factors. One of them is the matrix element between the ground state and the excited state, the dipole matrix element, and the other is the density of states. Now, this dipole matrix element is a property of the atom, and there's nothing that we can do to change that particularly. However, this density of states has to do with the environment, and particularly in the solid state, you have a lot of possibility to kind of tailor this environment using things like optical cavities and sort of pattern structures around it in general. And so, what I'll show you in this work is how we're able to basically make nanophotonic optical cavities around these devices that give us 1,000-fold enhancement of the density of states, so that changes this very, very small emission rate into something that we can totally work with, together with having a very high collection efficiency, and then with that, basically trying to move towards these applications of these rare earth systems. So I'll tell you first about these photonic circuits that we've developed and how we use them to control and manipulate individual rare earth atoms. We're actually able to do single shot spin readout optically through the cavity. And then in the second part of the talk, I'll tell you about this technique that we've developed to do very deep subwavelength addressing of multiple rare earth atoms. We've actually done this with 6 atoms at the same time, and how this is going to get us towards creating these strongly interacting arrays. And then in the last part of the talk, I'll tell you about how we can sort of exploit this freedom to use whatever materials we want to actually go and search for a variety of different crystals and other things to put these ions in to get different properties to pursue different applications. So okay, so the main starting point for this work though is having this is modifying the density of states to enhance this emission rate, and the key parameter there is the factor by which you do this, which is called the Purcell factor, and this depends on the quality factor of the optical cavity divided by the sort of mode volume. So the type of optical cavities that we use are one-dimensional photonic crystal cavities, and basically what these are, it's a Fabry-Perot cavity formed inside a single mode waveguide. You can basically understand this as light can propagate in one dimension in this waveguide, and by drilling a set of holes in the waveguide, we create an alternating high and low index pattern that makes a Bragg mirror. And if you put 2 of these Bragg mirrors together, you get a cavity in the waveguide. And the reason we use this type of cavity is that this the resulting mode volume, the size of the effective box sort of to which the photon is confined, is extremely small. It's sort of less than a cubic wavelength typically, but the quality factor that you can get in these things, especially in silicon, is still actually reasonably high. So this ratio is, I think, actually a few orders of magnitude higher in this geometry than in any other one. And so in theory, if you put in state-of-the-art numbers for silicon photonic crystal cavities, we should be able to get more than 1 million-fold enhancement, which completely solves this problem. The way we make these things is actually we prefer to make these optical cavities out of silicon because it's basically the best material to do that. It's the most transparent dielectric at this wavelength. But we put the erbium ions into some other substrate so that we have some freedom there to explore different things. And then to make it all work, we actually just sandwich these things together, and then the ions couple basically evanescently to this photonic layer. And in principle, this is suboptimal because they're not exactly at the maximum of the electric field, but the cost is only about a factor of 2, which when you're talking about trying to get to 1 million, doesn't really matter that much. So we make these things in our clean room out of silicon on insulator wafers, and lately we've been playing with making these very large-scale device arrays, not because we actually use all of these things at the same time, but because it gives you a lot of devices to pick from. But this particular device here has something like 100 optical cavities sort of distributed along this meandering waveguide. And then we use basically a rubber stamp technique after we fabricate these things in this SOI wafer to kind of lift them up and then drop them off onside the substrate, on top of the substrate doped with these rare earth ions. And we've gone through, then you have to get the light into these things. We've gone through a few iterations of how to do that. In our early experiments, we had these waveguides dangle off the edge of the chip, and then we brought in a sort of tapered optical fiber to get the light in, and this worked pretty well with reasonable efficiency, but this edge thing was a big pain in the neck. So in more recent experiments, we've actually come up with a grating coupler that couples near vertically incident light into the waveguide mode, and then we actually bring in an optical fiber that's been polished at the end, so there's total internal reflection of the fiber mode down into the substrate. So we can actually bring a fiber now in over top of the substrate parallel to it, and couple light in this way with about 50% efficiency. And the other thing that's really nice about this approach is that we attach this fiber to a sort of a carrier chip on which we pattern a coplanar waveguide that we can then put microwaves into, and then we can get this waveguide about 1 fiber diameter, like 100 microns away from where the spins are, and so we can use this to actually drive pretty fast, Rabi oscillations of the spins as well. And then this whole thing goes on top of a positioner stage. So fiber here on this attocube positioner, then we position it, bring it over this crystal that has these devices on it. And then this whole thing goes inside a helium-3 cryostat at about 0.5 Kelvin, which is the temperature we have to go to freeze out phonons that screw up the spin. And we have sort of a vector magnet here to apply magnetic fields. So this is our approach to making kind of cavities to really enhance this emission rate. But there's a couple of other approaches that people pursue that are also very interesting. In Andre Ferron's group at Caltech, they work on actually just directly using focused ion beam to just directly mill these same kind of one-dimensional photonic crystal cavities into the substrate that's doped with the ions, so they don't have all this transferring process and get slightly higher coupling strengths. Also, these Fabry-Pro cavities that actually were originally developed for atomic physics experiments by Jakob Reichel have also been applied not only to trying to look at single rare earth ions, but also NV centers and other kinds of systems. These have very, probably the next highest Q over V factor. Shoot, Keynote crashed. You guys just see my desktop now?
Yep, it happens.
So I'll just take it from the top. Just crashed again. So I think actually I'm going to skip that slide on purpose. The third technique I was going to mention is a very nice idea, which is that if you want to make your cavities out of silicon, you should just put the erbium directly into the silicon. And Andreas Reiserer's group at MPQ has some really nice recent results on that that you can just find on the archive. But nevertheless, this is what we're doing. So so it's back now, the screen. Okay. So so in our first experiments, the parameters are that we the host crystal that we're using is something called yttrium orthosilicate, which I'll explain later turns out not to be like a particularly good host crystal, but the reason we start with it is that it's a pretty well understood host material for rare earth ions. It's been studied in the context of lasers and quantum memories and things like that. So it seemed like a good starting point. And so we have our silicon cavities on top of that. These cavities are not quite state-of-the-art silicon cavities. We could get a few more orders of magnitude out of Q, but it is what it is. And so with these parameters, we expect that we should be able to get a Purcell factor of close to 1,000. And I should say also that the erbium ions are just doped uniformly into this substrate, and the density of them, between 100 parts per billion and 1 part per million, is such that we expect there to be between 100 and 1,000 within the volume of the optical cavity. So to go in and look at this, what we do is we tune the optical cavity to about where the erbium absorption resonance should be, and then we scan a laser basically, and at each frequency we send in short pulse of light and collect the fluorescence that comes out afterwards. And if we did this with sort of a bulk, a densely doped bulk crystal, you would expect to see an absorption or fluorescence spectrum that would look like this. It's kind of a typical inhomogeneous line within this crystal is a few gigahertz. But when we do this in our samples, we see instead of a continuous line, we see a series of sharp, irregular spikes, which you zoom in, they're only a few megahertz wide, and these are the optical transitions of individual erbium ions within this crystal. Spectrally separated by kind of random frequency shifts from inhomogeneous broadening, and you can confirm that these are actually single ions by looking at the G2, the intensity autocorrelation. They're very strongly anti-bunched. So to know how good of a job the cavity is doing, we can basically measure the Purcell factor directly by looking at the reduction of the excited state lifetime, and compared to the bulk value of 11 milliseconds, we get 17 milliseconds for this particular ion. So this is a factor of close to 1,000, which is in agreement with what we expected. And although this is among the largest Purcell factors probably ever observed in the optical domain, we definitely still have 1 or 2 more orders of magnitude to go by improving the cavities. And just to check that we're not fooling ourselves here, that we haven't somehow quenched the emission by putting these ions near the surface or something like that, we can check that this reduction in the lifetime really results from enhancement of the radiative decay by the optical cavity by just tuning the cavity away from the atomic resonance. And when we do that, we see that the decay rate of the excited state relaxes back asymptotically to something that's basically equal to the free space lifetime, plus or minus a factor of 2. So that's good. So next we'd like to go and explore the spin of these single erbium ions, and to do that we apply a magnetic field which lifts the so if you have a spin 1/2 ground state and excited state, you have 4 possible optical transitions. At 0 field they're all degenerate, but then we apply a small field and they split into 4 lines, and so this is how we can go and probe this spin. Something that's a little funny about this sort of the solid state and rare earths in particular, where you have so much spin orbit coupling, is that the magnetic moment that describes how much do these states shift when I apply a magnetic field is very strongly anisotropic. So in this plot here, we have here a constant amplitude magnetic field that we rotate in the plane, and you see actually the splitting between these optical transitions very sort of by more than an order of magnitude as a function of the angle, and it's sort of described by this anisotropic magnetic moment tensor here. So it's kind of weird. Okay, so with this, so now we want to go and measure this, actually try to measure the spin. And so to do that, we have these 4 transitions, and we'll call these 2 of them A and B spin conserving, because you excite to the same spin excited state, and these 2 spin flipping, C and D. And so to try to measure the spin, what we'll do is excite on the A transition and then on the B transition, and then A and the B, and collect photons after each of them. And the theory here is that if you hope that when you go up to the excited state, here you come back down to the same spin state most of the time, and so you should be able to scatter a few photons here or a few photons here, depending on which spin state you start in. And if you repeat this sequence many times, on average you get the same number of photons following each kind of frequency excitation pulse, because there's no reason for the spin to be polarized one way or the other. But if you go look at an individual time trace, a single time trace from a single run of this experiment, each line here is a single photon click recorded after either an A transition or B transition. You see that the system sort of toggles back and forth between periods where you're getting more one color or the other. And so this is quantum jumps of the spin, basically going back and forth between one spin ground state and another. And if you kind of infer the properties from here, you can do sort of a Bayesian reconstruction of the spin state as a function of time, and really watch these quantum jumps, back and forth on on a pretty actually human time scale. You could listen to these clicks in the lab. If you want to think about this from a quantum information perspective, if I said, okay, well, I have a spin at some time, and now I want to measure what it is, there's a fidelity associated with that. And by sort of applying an adaptive maximum likelihood measurement strategy to this, we figured out that we can do that measurement with an average fidelity of about 95%, and it takes 20 milliseconds. So basically, we need to get about 2 photons to be that confident in what the spin state is, and our count rate is such that takes that long. So we can do, this 95%, we can do on average sort of 20 consecutive independent measurements before the spin flips. And this is actually pretty good. It compares favorably to prior art in the solid state, which is about high 90s for diamond color centers, although actually there's a recent silicon vacancy work from Misha's group that's many 9s here. And in quantum dots, this is actually not quite this good. So, and we think that we can improve this, get it a little faster and a little higher fidelity by basically improving the classical collection efficiency here a little bit. And at this point, I want to point out that Andre Ferron's group had a paper on doing very similar measurement things that appeared around the same time as ours, with a terbium ions, a terbium rare earth ions in a solid crystal, a terbium 3+. So that measurement works really nice, and it actually basically worked the first time we tried it, but then we actually sat back and thought, well, okay, in order to be able to detect, we can detect here maybe, I don't know, 20 or 30 photons before the spin flips, but we only collect a few percent, so actually the atom would have to scatter maybe 1,000 photons before flipping the spin to do that. So you really need a cycling transition to do that. That doesn't happen by accident. But the thing is that with the spin 1/2 ground state and spin 1/2 excited state, you actually generically don't expect to have a cycling transition here, because there's no angular momentum conservation to sort of dictate that with an electric dipole transition or even magnetic dipole transition, you should come back down to where you started. So why does this work? And so we thought about it, and we kind of came up with a hypothesis that it's actually the cavity that is making this work in the following way. Each of these transitions, the spin conserving transition and the spin flip transition, has a polarization of its dipole moment. And when you put this in a cavity, it's possible for them to actually couple differently to the cavity. And these photonic crystal cavities, it's important to say, are sort of polarization non-degenerate. So effectively, we have only a single polarization mode in the cavity. It's approximately linearly polarized. So if you set up your sort of spin quantization axis such that the dipole moment for the spin conserving transition was parallel to the cavity polarization, but the dipole moment for the spin flipping transition was perpendicular to the cavity polarization, then this transition would not be enhanced by the cavity at all, and this one would be enhanced by the cavity sort of maximally. So even if in the absence of a cavity, the decay rate of these two transitions was equal, now inside the cavity, this one is going to be basically be enhanced by a factor of this Purcell factor, which is of order 1,000 here. So you could induce a cyclicity of order the Purcell factor of order 1,000 by lining up your dipole moments this way, even if you didn't have that in the bare atom. And it's if we had a spherically symmetric atom, the condition for doing this would just be that your magnetic field defining the quantization axis would be parallel to the cavity polarization. It turns out, with this crazy G tensor, it's not so obvious, but you can actually prove that it's nevertheless always possible as long as you have a linearly polarized cavity. So to kind of check this hypothesis for what's going on, we went and measured this cyclicity, which is we define as the number of photons you can scatter before you flip the spin, as a function of the angle of the magnetic field that defines the quantization axis. And you can see that it has, let's say, quite a lot of variation. And this model here is actually something that has it takes these G tensors as input, these anisotropic G tensors as input, and it has only two free parameters, which is basically the relative angle between the cavity polarization and the dipole moments at some orientation. So this is pretty clear that this is what's going on. And to really check that that it's not still somehow by accident that the free atom, the erbium atom by itself has a really high cyclicity, we actually measured a series of ions with different Purcell factors, and then also deliberately lowered the Purcell factor of one ion by detuning it. And you see generally this cyclicity varies linearly with the Purcell factor. So based on this, we kind of conclude that as you would expect for a spin 1/2 system, these erbium ions by themselves have no particular selection rules. You should only be able to scatter 1 or 2 photons. But this cavity now not only is really enhancing the emission rate for us, but if we set up the magnetic field right, doing it in a very spin selective way, and that gives us the cyclicity that we need to not only see these things, but also to do this single shot readout. So this might be a good first place to pause for questions.
Great, Jeff. Sounds good. So we got a couple lined up here. So the first one is from Parth Jatakia, who asks, what are the properties required in a material for it to be a host crystal for the rare earth islands?
Yeah, that's a great question. And the last third of my talk is going to be about that. So I'm just going to postpone that for now.
Okay, sounds good. The next question comes from John Simon, and it is there any conservation law that says that since the rare earth ions are less affected by the environment, they can scatter less? So in units of the inhomogeneous broadened cooperativity, nothing got better?
So I haven't used the word cooperativity. And the cooperativity is, even though this Purcell factor is 1,000, the cooperativity here is 10 to the minus 3.
Got it.
So
another question from Dan is Dan Stemper-Kern is these rare earth atoms have an open shell. I think of open shell atoms as being particularly susceptible to external fields because the electrons in the open shell can reconfigure in response. So why is it that these open shell atoms are also still insensitive to fields like electric fields or strain from the surrounding crystal?
Let's see, they can reconfigure. So they do. I mean, in some sense, this crystal field splitting is that they are reconfiguring. But then, for example, if I just think about these two lowest spin levels, those are actually protected by time reversal symmetry. That the electrostatic perturbations can't affect them anymore. So all the damage that electrostatic effects can do has been done already, and then they're left alone after that. As for whether the sort of, let's say, the relative energy of some ground and excited state should be more or less affected by this, I mean, it is true that you can often have a sensitivity there. I don't exactly know what to make a comparison to say whether it's more or less sensitive, except to observe that in bulk crystals, people have observed sort of optical dephasing rates at sort of the kilohertz level, which is pretty darn small.
Okay. Another question here is from Dima Butker, and it is, can controlling the lifetime with an electric field be useful?
So I'm going to guess that controlling the lifetime with electric field means you maybe try to apply a really big electric field to mix some opposite parity states to shorten it more, and something like that would be really neat to do. It's probably hard in the kind of with an electrode to apply such a big electric field, but you could imagine trying to find host crystals where you have more of a forced electric dipole moment from having a very low symmetry site. Although there would be a cost to doing that too, which is you now have a permanent electric dipole moment that would make you susceptible to spectral diffusion.
Okay, and let's ask one more question here and then we can continue. So this question is from Christopher Anderson, and it is, why are the A and B transitions different frequencies? Is the G factor different in the ground and excited state, or is it something else, such as the crystal field?
It's the G factor is different.
Cool. Okay, why don't you keep going, Jeff?
Okay. So yes, okay, so armed with this ability to go and probe the spin, now we want to go and measure the spin properties. And so the first thing to measure is the spin T1, which we do actually just by performing, an initialization, one measurement, waiting a time, doing another measurement, and then seeing if they're the same. And this measurement here shows about a 45-second T1, so this is pretty long. Which is nice. But then we actually went, what we expected is this would be limited by spin lattice relaxation, which is that the spin, gives up either exchanges energy with the phonon bath, basically. And the spin lattice relaxation in these types of rare earth ions is actually pretty well understood in terms of the functional dependence it should have on both temperature and magnetic field. And in the regime where we are, it should have this b to the -4 dependence. So it should basically get longer as you go to lower fields. But when we went to measure this, we found, not only did it not lie on this curve, but actually it's totally completely different, crazy functional dependence. So this is clearly not the right theory. So we try to think about what it could be. And one hypothesis is that, well, we actually have not just one erbium atom, but a lot of atoms in this crystal. And maybe they're actually, the way the single spin that we're looking at relaxes is actually by flip-flopping with the neighbor, which would actually be nice because it would be beginning to get into the regime of having interacting systems that we'd like to go to. Now, given the density that we have here, we actually expect that the sort of the kind of the typical actually dipole-dipole coupling rate between average space neighbors would actually be closer to a kilohertz. So in some sense, that's too fast, but then these things are detuned from each other because the local magnetic fields from nuclear spins kind of inhomogeneously broaden the spin transition. So it's a little hard to say what you expect it to be. But our hypothesis is maybe that it is these flip-flops, and some additional support for that comes from the fact that we actually see a lot of heterogeneity. If we look at different ions and different samples, you see different functional dependencies and also vastly different rates by sort of 2 orders of magnitude. But to really pin down or to really test this conjecture that it's flip-flops, we do sort of an experiment where we actually try to use this single ion to polarize the bath of erbium spins around it. And the way we do that, in the experiments I've showed you so far, when we probe alternately on the A and B transitions, we effectively keep the spin that we're looking at in sort of an infinite temperature state with no average spin polarization because we just are pumping it back and forth. So if you thought that it was flip-flopping with its neighbors, then also all the neighbors should get into this infinite temperature state. And that's sort of the best state to be in if you want to flip-flop because you've always got neighbors that are in the opposite state to flip with. On the other hand, if we change our measurement strategy so that we only ever drive on this B transition, then we generally polarize the atoms into the spin up state, the ground state of the A transition. Every now and then they flip back into this state and we get a burst of counts, and that's how we can still measure what's going on. But in this case, you keep the atom polarized, and so you would think that it would also be polarizing all of its neighbors, and then the flip-flop rate should be lower because it doesn't have any neighbors in the opposite spin state to flip-flop. And so if we measure actually the T1 in these two cases, we do see that when we polarize everything, the T1 is substantially longer, and that the sort of the enhancement goes up at low fields where these flip-flops are apparently more pronounced. So based on this, we're pretty comfortable concluding that the T1 is limited by interactions with its neighbors, which is, I would say, promising for getting into this regime of making interacting systems. Then we turn to doing coherent manipulation of the spins by sort of driving we drive Rabi oscillations with microwaves in between an initialization and a final measurement. And those are Rabi oscillations. And then the coherence time we measure with either Ramsey or Hahn echo. And these numbers are not as good as the T1, I would say. The Ramsey T2 time is about 100 nanoseconds. The Hahn echo T2 time is more like a few microseconds. And although it's not as good, we actually are it's completely clear what this comes from, and it's the fact that this yttrium orthosilicate material has a bunch of nuclear spins in it. In particular, yttrium has every single yttrium atom in there has a nuclear spin 1/2, and so that gives you a kind of a few Gauss random magnetic field. and that's what's responsible for sort of this dephasing. Now, the nice thing about this nuclear spin induced dephasing is that it's slow, so you can get away from it pretty effectively with dynamical decoupling. And so by using this sort of so-called CPMG sequence where you do pi over 2 and then pi until the cows come home, we're actually able to extend this coherence time up to a few hundred microseconds with sort of no apparent saturation. Which may be good enough for some things, but we'll come back later to talk about how you'd really like to pick a different material without nuclear spins to really get around this problem. But I think, yeah, and then actually but doing these experiments also gives you kind of another interesting window into what goes on in the solid, because most of these ions show pretty boring kind of Gaussian Hahn echo curves, which is what you would expect from some bath of many nuclear spins, but actually every now and then you find one where you actually get a pretty weird spiky oscillatory signal in the dynamical decoupling spectrum, which looks a lot like maybe you have hyperfine coupling to just one nuclear spin that's sitting nearby. And since all the yttriums are there all the time, this would probably have to be like a silicon-29 or something like that in the crystal. And so this is sort of an interesting thing, both to try to understand how it limits the coherence, but also to study sort of in and of itself. Okay, so now I'm moving into the second of three very unequal length parts of my talk, which is how we extend these techniques that we've developed to control and manipulate single rare earth atoms in this crystal, and actually extend them to control many atoms at the same time, where these atoms are very close together. So let me take a step back another way. So in a lot of atomic physics experiments, if you have a quantum gas microscope or an array of atoms and optical tweezers, the way you address atoms, the way you sort of label atoms, this is atom A, this is atom B, is by their spatial position. So where on the camera your photons show up is how you know which atom they came from, and that works really nice because it lets you use cameras. But the downside of that is that if your atoms get closer together, then the diffraction limit of whatever imaging system you're using, you can no longer resolve them from each other. So particularly in the solid state, and this is how actually most NV experiments work also, but particularly in the solid state, to get these strong interactions, you would actually really like to be able to bring atoms much closer together, say more like tens of nanometers, which is hopelessly far below the diffraction limit. So there's a couple of other techniques that people have explored with NV centers, like using different orientations to maybe address one is easy, 2 or 3 spins below the diffraction limit. But what is really neat about these rare earth ions is that we can actually use this inhomogeneous broadening to address a very large number of atoms below the diffraction limit by not thinking about them as having a particular position in space that we use to resolve them, but actually a particular position in frequency for their optical transition. So we resolve these things based on their optical transition frequencies. And so I showed you this sort of spectrum of a device before, but you have a kind of a few hundred ions here with their transitions spread out over a few gigahertz. And now basically by actually using just one laser with sidebands generated from an EOM, we can basically change which of these guys we talk to. And so kind of go through and initialize and read out and manipulate a large number of these atoms in rapid succession in the frequency domain. And there's a few hundred ions here. We've actually only been able to control these relatively isolated ones out here in the tails because it's too congested here for now. But all of these ions are within an incredibly small subwavelength volume here. So we're not using any spatial information at all to do this. And in principle, there's the potential to do this with a very large number of ions, although 6 is already not so bad. In principle, actually, the number of ions that you can do this with is limited by sort of the number of spectral addresses you have, which is the single ion line width divided by the sort of inhomogeneous width here. And this is pretty easily 10 to the 3. And maybe you can get it to be a little bit bigger in the system, but 1,000 is a pretty good number. Of course, this ratio, you can compute this ratio for things like quantum dots or NV centers, and actually you get a similar or even bigger number. But what's really unique about the rare earth atoms is sort of an NV center is this kind of inhomogeneous line width is maybe 10 terahertz. And so what that means is that to be able to address different centers, you almost certainly need 2 different lasers. And if you want to do 3, you need 3 lasers and so on. What's really unique about these rare earth ions is the overall kind of narrow scale of this inhomogeneous broadening and correspondingly the homogeneous line widths. Lets you do all of this with just sidebands on a single laser. So it's sort of very practical to scale this to very large numbers. Okay, so to be able to do this, we need to have this kind of high cyclicity for all the ions, and sort of generally we can do this because they sit at places in the cavity with similar polarization. And then here are sort of photon count histograms showing how we do this for the first 2 ions we look at. We can do not quite as high, but sort of here like 75 and here 85% fidelity single shot readout for these two ions. And we're really doing this at the same time, just alternating which one we drive. We can initialize them into the same state and then drive Rabi oscillations, or initialize them into different states, drive Rabi oscillations. To do, of course, the microwaves that drive the Rabi oscillations address both the ions equally, because the diffraction limit for microwaves is even bigger than the optical transition. But we can actually use optical techniques to do some spin control using the AC Stark shift, basically by tuning our laser close to the transition of one ion, but not the other. You can put a local phase shift on it. So we measure this by putting some optical pulses interleaved with some dynamical decoupling sequence, and you can see that we basically, kind of a Ramsey measurement, pick up a phase shift from having these optical pulses. Sorry, the red curve here is without optical pulses, and the orange is with optical pulses. And then we can actually, for these two ions, have one of them has their A and B transition frequencies here, the other here and here. And by sweeping the sort of the frequency of the laser that we use to generate these phase shift, you get kind of exactly the dispersive sort of profile of this phase shift that you expect. And so of course, the closer to resonance you go, the bigger your phase shift is, but then also the more scattering you get. You get sort of 1 over delta phase shift, 1 over delta squared scattering. But there's pretty good working points that we can choose out here, where for the kinds of optical powers we can do, we can get pi over 2 phase shifts with only 1% or so loss in kind of the coherence visibility. So essentially, the way, from a kind of a quantum information perspective, you want to think about this phase shift as being a Z rotation, and it's basically selective which ion we put it on. With two ions, we can get a differential phase shift with just one frequency. If we had n ions in general, we would need to apply light at n-1 frequencies to get sort of orthogonal control over the rotation angle for all n ions. But Z rotations are actually not enough for you to do complete control over a qubit. You need to be able to do rotations around 2 different axes. And so we can do that by kind of compiling this optical Z rotation together with some microwave pulses. And we've shown here how to do that basically in a way that lets us do sort of effectively an optically controlled X rotation. Here we rotate one ion while the other one is left alone. And then by flipping around how we do the microwave pulses, we can rotate the blue ion and leave the orange ion alone. So we can convert these Z rotations locally into local X rotations. It gives us complete coherent control locally over each ion. And then lastly, to kind of show how far you can push this technique, we went over here to look at this group of 4 ions, and again, we're able to do sort of simultaneous single shot readout with an average fidelity of 80 or so % on these, drive simultaneous Rabi oscillations on all 4 ions. Actually, the Rabi frequency is a little bit different for this one, because it turns out it's sort of upside down in the crystal with respect to the others, so it couples differently to the AC field. And then if we really try to simultaneously initialize all the atoms in one state and then read out all 4 atoms, we see that the sort of the probability that we get all 4 ions right in the same single shot is about 50%. So it's a pretty, which is about 80% to the 4th power. So we have pretty reasonable sort of multi-qubit control in the system. So the thing I think to me that's really promising about this is the fact that all this addressing was completely without regard to the spatial separation between the atoms. So if we could now get them closer together, then we could have a strongly interacting system, and that would be a lot of fun to play with. In our current devices, where we have the ions everywhere, uniformly distributed throughout the sample, their average spacing is such that the average interaction is about 1 kilohertz, which is not big compared to the coherence time that we have because of these nuclear spins. So we're not really able to actually see interactions between these guys. But what we would like to do in the future is come up with a technique to start out. And if we put more ions into the crystal, just had denser doping, then we could get them closer together on average and boost up the interactions. But you see, we already have the problem that the spectrum is too congested here, and we can't address most of the atoms. So what we really need to do is sort of simultaneously bring them closer together and have fewer in the cavity. And the only way to do that is to actually change the way we get them into the material in the first place, and that's to say, start with a material that has no ions in it at all, and then kind of controllably, perhaps through ion implantation, put them just in a small region that's much smaller than the cavity. So we have a local high density, but globally a small number. And with this kind of technique, with kind of what you can do with ion implantation, it should be pretty easy to make a cluster that's like 10 or a few tens of nanometers wide and get a few tens of atoms in it. And then we really should be able to essentially, resolve all of this spectrum should be sparse enough that we should be able to talk to all of them at the same time, and they would have these sort of megahertz scale interactions. So in the remaining few minutes, I want to talk about the host material, like like Parth asked about earlier, which is okay, so the thing that's actually kind of stopping us from actually doing interactions or going and making single photon sources and quantum memories for quantum networks is basically that there's some noise in the system. And this is not a big surprise. That's what you expect in the solid state. But actually, like John's question, our optical transitions are actually not radiatively broadened. There's some kind of spectral diffusion that's, even with our Purcell enhancement, still about a factor of 100 on top of the radiative line width. And the spin T2 is not particularly long. That comes from the nuclear spins. And not being able to control this density is kind of annoying in terms of being able to realize interactions. These problems, actually, they're not erbium specific problems. Really, they're problems of the crystal that we have erbium in. And so now the really nice thing about the system is we can just go put the same erbium that we know how to use and put it into a different crystal and then build everything we've done, we keep, but we can move ahead with, hopefully less noise in this crystal. So you can get rid of magnetic noise, maybe pick a different site symmetry so you don't have a permanent electric dipole moment that makes you really sensitive to spectral diffusion from charge noise, something where you can kind of control the dopant positions better. And maybe there's other problems that we don't even know about yet. So in another effort in my group, we're kind of working on fixing this problem. So there's three real problems with this host crystal. One is the nuclear spins. The other is that it has a very low site symmetry. So there is a permanent electric dipole moment, and that's probably responsible for the spectral diffusion. And it actually turns out, even if we wanted to get less erbium in the cavity, we can't. The quantity that we have in these crystals is basically the trace concentration of erbium that exists in yttrium when you buy it. So the people who grow our crystals buy the purest yttrium they can get. It's 100 parts per billion erbium in it. That sounds pretty good, but that's too many if you're counting single atoms. So what we would really like to have if we were to design a new material is something that doesn't have nuclear spins, has symmetric enough sites that you don't have a permanent electric dipole moment, doesn't have any rare earth elements in it at all, so you don't have this contamination problem, and then something that we can then put them back in with ion implantation. And there's about 40 well-known materials that meet this criteria, although an undergraduate student in Bob Kava's group got interested in the question of exactly how many less well-known materials are there, and there's this many. It's sort of an interesting data mining project, but it's a kind of a countable number to go and explore. And this nuclear spin thing is the biggest cut that you take. And what I've shown here is the color-coded atoms in the periodic table are those that have stable isotopes with non-zero nuclear spin. And you basically see that it's all the even columns that you can use. Okay, so to do this, we have kind of this work, I should say, is a collaboration with my colleagues Natalie De Leon and Steve Lyon and EE and Bob Cavos, materials chemist in the chemistry department here. We basically find pure substrates and then try to do as much bulk spectroscopy on it as we can, and only at the end of the day go try to look at single atoms because that's very tedious compared to bulk spectroscopy. And so we started implanting, we got maybe 10, 15 different materials and started implanting erbium into it. And basically everything works. You can see erbium in essentially everything. The first material that we characterized extensively was rutile, TiO2. And what really caught our eye here was that actually the inhomogeneous line width of the implanted ions is actually narrower than the sort of as grown samples that we were using for yttrium orthosilicate. So this shows that you can actually still have nice properties for these rare earth ions, even if you introduce them in the pretty violent way that you ion implant them. And I won't spend too much time. By using electron spin resonance, we're actually able to sort of figure out the site symmetry and determine where it is in the crystal. And the particular site that it sits on actually is a pretty symmetric site with the point group D2H, which tells us that it doesn't have a permanent electric dipole moment. So maybe, which would mean that it shouldn't have a transition shift from electric fields. So maybe that's part of why we have this narrow inhomogeneous line width. Another question is, for every ion that you shoot in, how many actually sort of activate, by which I mean go to the right site in the crystal where they're going to have exactly the transition wavelength that you're looking for. And when you first implant them, the answer is, most of them don't. But actually, if you anneal it in the right way, actually the fraction that appear to be activated is consistent with unity, I would say. So this is, again, really promising for being able to kind of create a cluster of spins where they're all doing what you want. And as you anneal, you can see that you remove damage from implantation. The line width narrows up, and all that is sort of what you expect. TiO2 is not the only thing that looks good. We have also nice results from a few other materials. MgO is a random one I've shown here. We've lately started taking these really cool two-dimensional spectra that make it much faster to analyze all of this data because you have a few 8 ground states, 7 excited states, and you can have a few different sites in the crystal. So it's very easy to get hundreds of lines that can show up in this spectrum. But in this kind of 2D way, you can kind of figure out pretty quickly what's going on. And the last kind of direction that I want to mention that is not something we've started working on yet, but I think is maybe thought-provoking for what you can do with this is actually maybe instead of using solid crystals like knock on knock on glass kind of crystals, if instead you tried to put these atoms into molecules. And the advantage of doing that would be that now you could use molecular synthesis techniques to actually make, ordered arrays of these things. And that would, which is something that it's actually pretty hard to imagine getting around with ion implantation into solid crystals. Ordered arrays where you can kind of control the spacing at the angstrom level. And there's a little bit of precedent that makes this seem really promising. So first of all, in the single molecule magnet community, people have actually been making organometallic complexes with lanthanide atoms for a long time. And there's some literature that suggests that you can have a spin T1 of thousands of seconds of erbium in particular, erbium specifically, in organometallic complexes at low temperature. So again, this is here, you want to think about this as the isolation of the 4f electrons, again, keeps whatever floppy stuff is going on in these molecules from affecting the spin. And then a more recent thing that's actually very promising is from a collaboration between David Ausschlam and Dana Friedman in Chicago and Northwestern. They have put not a rare earth metals, but a transition metal, chromium, into organic complexes, and actually been able to observe ODMR, optically detected magnetic resonance, in the system. So sort of again suggests that this is a promising direction, and this should probably work, I would say, better with rare earths. But that's my hobby horse. Okay, so with that, I'd like to summarize, the parts of my talk. I showed you about how we make these photonic circuits that let us control and manipulate individual rare earth atoms, including doing a lot of this stuff for the first time with erbium, and getting single shot readout. And then we have this sort of very nice technique for addressing many atoms with a sort of a deep subwavelength spacing that's promising for realizing strongly interacting systems. And then an effort to develop new materials, new ways of trapping these atoms, basically to actually enable these applications to really work. With that, I'd like to conclude by thanking the group that did this, our funding support, and then also thanking all of you for your attention.
All right, Jeff, we got some questions here. So the first one is from Hannes Bernian, and he asks, let me pull the screen over here. Do you excite and detect through the fiber, or can you also do free space?
We do not have any free space optics.
Cool. That was quick. Okay, the next question comes from a pair of people, one of which is myself, the other is Wenchao Xu, and that is, can you do specific pulse shapes to isolate the effective interactions on the coherence time? So I think there are these like Wahuha or something pulses that have been performed in, say, the polar molecules experiments.
Yes, and things like that would let you isolate the effect of electron-electron interactions on the electron T2, but we actually don't think that electron-electron interactions are anywhere close to affecting the electron T2. So the electron T2 is affected by nuclear spins, and in some sense, the Hahn echo already is showing you that it's affected by something that is changing slowly, but not that slowly, which is probably nuclear spins. But the electron-electron interactions, we really hypothesized affect T1. But because the T1 is so many orders of magnitude longer than T2, it's really, I think you really need to think about that as an incoherent process. It's not really that there's coherent flip-flops happening, but it's kind of random jumps that happen. So I think these decoupling sequences wouldn't do anything that your nuclear spin-induced dephasing wasn't already doing.
Got it. Okay, the next question here is from Dima Budker. It's also a statement. The statement is, "This is a really nice system!" Exclamation point. However, the requirement of deep cryogenics would presumably hinder practical applications. What are the highest temperatures at which rare earth ions and solids could still be usable?
So the even electron ions like praseodymium and europium, where you have no electronic magnetic moment in the ground state, and so you just have this nuclear spin, you can work up to like maybe 6 or 7 Kelvin with those. And that's kind of the workhorse quantum memory system. However, the odd electron Kramer's ions like erbium and terbium and neodymium, you need to be pretty cold. In fact, the spin lattice relaxation rate, I showed you this b to the 4th dependence, but the temperature dependence is actually t to the 9th power. Which is nuts. And so we actually did our first experiments at a 4 Kelvin cryostat, and we could see all the optical stuff really nicely. We couldn't see any spin, anything, no optical pumping, no nothing, which meant that spin T1 was shorter than, probably shorter than about 10 microseconds. But then we just bought this cryostat, which is 10 times colder, so you pick up a factor of 1 billion, and that's fine. But that's pretty unforgiving. So even 4 Kelvin, even 2 Kelvin is probably too hot.
Cool. A couple more here. So from Yasser Salani, how deep are the ions in the crystal? Is there any charge fluctuations that affects those ions close to the surface?
Yeah, so we don't, they're within the top 100 nanometers probably based on the coupling strength of the cavity. They can't be any deeper than that. And almost certainly there is something going on. So for bulk erbium in this yttrium orthosilicate specifically, people have measured at low temperatures optical transition coherence times of order, tens of milliseconds. About a millisecond using sort of photon echo spectroscopy. The coherence times that we see, inferred from these line widths are more like tens or hundreds of nanoseconds. So we have many orders of magnitude more noise than you would have deep in the bulk. And we have not really begun to play with that, but I would say the playbook from NV, so NV centers have this problem too, and NV centers work great deep in the bulk in terms of having narrow optical transitions, but when you put them in devices or bring them close to the surface, the optical transition line widths go to heck. And the one fix there was just to switch to the silicon vacancy center, which is now inversion symmetric, so it doesn't have a permanent electric dipole moment, so it's not sensitive to first order to charge noise anyways. And you can maybe do that and suppress your noise, that would be better. Anyways, here, that playbook is even simpler to apply because erbium, itself is spherically symmetric. So the only reason it ever has a permanent EDM is if it's on a low symmetry site. So by looking at different crystals, like for example, this TiO2 that are not have a nonpolar point symmetries, we should be, that's my main strategy, is to try to suppress the sensitivity to field noise that way.
Got it. The next question comes from Andre Ferron. He asks, do you see any degradation of the erbium in the tail of the inhomogeneous broadening?
Hi, Andre. No, not at the level of like 10 gigahertz. I think we maybe have seen some weird stuff if you go out like 30 gigahertz, but I would say generally no.
Got it. Okay, and then there are several questions that maybe I'm just going to group into one and ask in a more general way. Sort of what do you think are sort of the ultimate limits on scaling this frequency multiplexing scheme? Like how many ions do you think you could get to if you sort of have sort of everything that you need to sort of optimize in this direction?
Yeah, that's a good question and something we spent a lot of time thinking about. So I think if you want to do, so right now, I call it simultaneous initialization and readout. It's actually sequential, but in a very rapid fire sense, where we go from one ion to the next on a time scale much shorter than T1. So for all intents and purposes, it's sequential. But if you went to, but it's, say a few tens of milliseconds per ion. So if you try to do 100 ions, eventually it would get pretty slow. However, that's not fundamental. Actually, there's no reason you can't do this in parallel. Send in multiple frequency tones at the same time. For optical pumping, that's totally straightforward. For the readout, you would either have to kind of filter the photons, or if you got into a high cooperativity regime, you could do sort of coherent reflection measurements on the cavity. But so if you can parallelize this, I think there's actually, for the initialization of readout, I really don't think there's a limit. So as long as you don't have as long as you can discard spectrally overlapping ions, I think 100 is not a very big deal. Now, the same statement does not really apply to the this coherent control, because there, you need to get, as you go from trying to do Raman transitions, whatever that is, you need to get to a pretty big detuning in order to have a high fidelity coherent control. But of course, if you go to very big detuning's big compared to the spacing between ions, then the differential rotation between ions is not very much. So you lose your addressing. So there, I think we've kind of estimated that if we can narrow up these lines a little bit and use the full inhomogeneous distribution, sort of it depends on what fidelity you want, but kind of 10 to 30 is maybe achievable. However, there is another angle there, which is actually that that it turns out that for reasons that we're still trying to understand, the spin transitions themselves, the microwave transitions, are also pretty disordered. And this is maybe variations in the G tensor from nearby strains. So if that disorder turns out to be pretty big, you could actually imagine doing the same kind of spectral addressing on the microwave transitions, and then that would be better.
Got it. Cool. Thanks. All right. In the interest of time here, I think we will conclude, and I'll pass it off to Shimon, who will say something.
Okay, thanks, Jeff, for a great talk, and thanks, Adam. So let's see, I'm going to just show this slide here. Hopefully you can all see that. So next week, I want to say that there is no VAMOS or quantum science seminar. because of DAMOP. So next week is DAMOP, and I'd like to encourage everyone to register and participate. It's free, and registration is now open. But in 2 weeks' time, we will have another Vamos talk from Jakob Reichel of Sorbonne University. And I also want to advertise our European sister seminar, the Quantum Science Seminar. And in 2 weeks, there'll be a talk from Thierry Giamarchi. So hope to see you all at DAMOP virtually, and then also in 2 weeks for our next Vamos talk. Thanks a lot, everyone. And thanks again, Jeff, for a great talk.